next few minutes, you're going to see 8 brand new James Webb discoveries, including a chemical recipe for future planets, star clusters from the universe's infancy, and a galaxy so distant Webb may have caught it only 290 million years after the Big Bang. No recap, no filler, straight to the evidence. A lot of people are tired of the latest JWST discovery videos that waste half the runtime retelling Webb's original story. So we're not doing that. This is an update, not a history lesson. And because we're moving fast, all sources and papers are linked in the description, so you can dive deeper after the video. Also, one more promise. We'll keep speculation on a short leash. If the data doesn't show it, we won't pretend it does. All right? Discovery 1. Jupiter's upper atmosphere isn't boring at all. Webb has looked at Jupiter before, but this time the focus is higher than you'd expect, the upper atmosphere above the Great Red Spot. And instead of a smooth, calm layer, Webb saw structures, dark arcs, bright regions, patterns that shouldn't look that messy. That matters because the upper atmosphere is where you'd expect things to be simpler. Thin, less chaotic, less weather. But the image suggests there's more energy being pumped upward than we assumed. Possibly from sunlight interacting with chemistry, and from wave-like motions moving through the atmosphere. These are gravity waves, not gravitational waves. Gravity waves are more like ripples you'd see on water, except in gas layers of a planet. Gravitational waves are space-time itself shaking after massive objects collide. Jupiter's atmosphere is basically telling us your models are missing something. Number 2, a 3-star system that secretly contains 4. Next, one of those discoveries that feels small until you realize what it changes. A star system called WL20 was thought to contain 3 stars. Webb's resolution shows one of those stars is actually a tight pair, a hidden binary. So the system is likely 4 stars, not 3. Why do we care? Because the number of stars changes the gravitational environment, and that changes how disks behave, how jets form, and how planets might assemble. If you want a clean, simple nursery where planets form peacefully, a multi-star system is the opposite of that. And yet, Webb can see disks and jets around components of this system, meaning planetary formation may still be happening in a place that should be too chaotic. It's a reminder that the universe doesn't build solar systems in the easy mode we imagine. Number 3, the richest hydrocarbon chemistry ever seen in a planet-forming disk. Now we jump from what's out there to what could eventually become us. Webb studied the disks around the young star and split the light into a spectrum, basically a chemical barcode. And what that spectrum revealed is wild. The disk is loaded with hydrocarbons, a rich set of carbon-based molecules, including detections that are extremely rare outside of our own solar system. These aren't life-detected headlines, let's be crystal clear. But this kind of chemistry that can become a raw material for complex worlds because disks are where planets are built. So when you see a disk with a chemical profile this deep, it's like finding a kitchen stocked with ingredients. Not a finished meal. Not proof dinner will happen, but a clear signal the environment is chemically capable of producing complex outcomes. This is the part audiences love when you keep it grounded. Webb isn't announcing aliens. It's showing the pathway, how nature sets the stage. Number 4, the Serpens Nebula, a star factory in high definition. This might be the most visibly satisfying discovery of the list. Webb imaged the Serpens Nebulae, a star-forming region where newborn suns are emerging inside dust clouds. And what makes this image powerful isn't just pretty colors, it's structure. You can see aligned jets, material being fired from young stars like cosmic exhaust pipes. You can see dark lanes, dense dust blocking light. You can see shapes that look almost carved. This is what viewers mean when they say, show the subject information, show the pictures more than your face. Because images like this are the story. And the story is simple. Stars are born violently. They don't drift into existence. They blast their ways out of chaos. If you like this fast, evidence-first style, subscribe. BackSpace updates you on what Webb is actually finding without turning every result into a hype machine. Number 5. A deep field where gravity turns the universe into a magnifying glass. Alright, this is where Webb becomes almost unfair. A new deep field image shows a massive galaxy cluster in the foreground and countless more galaxies behind it. But the foreground cluster is so heavy it bends space-time, causing gravitational lensing. That lensing stretches background galaxies into arcs. And more importantly, it can magnify extremely faint objects that would otherwise be invisible. And this is where Webb pulled off something incredible. In those lensed arcs, researchers can pick out star clusters that already existed very early in cosmic history. This is the kind of discovery people are actually watching for. Not Webb is amazing for the 1000th time, but here's what Webb can see now that we couldn't see before. Number 6. Star clusters, just 460 million years after the Big Bang. Let's zoom in on that. The universe was only a few hundred million years old, still in its cosmic childhood. And yet Webb reveals organized clusters of stars. That means structure formed fast. And that's a big deal, because early structure ties into the bigger question in cosmology. How quickly did the first generation of stars ignite? How quickly did galaxies assemble? How did early light begin transforming the universe? Webb is essentially pushing our timeline backward, forcing our models to explain order sooner than we're comfortable with. And that is exactly why some viewers comment, "This is big," because it is. Not in a clickbait way, in a the equations have to keep up way. Number 7. The Crab Nebula, a 1,000-year-old explosion, reanalyzed. Now we come closer again to something famous, the Crab Nebula. It's the debris of a supernova observed around the year 1054, a star that ended its life in a blast powerful enough to be recorded by humans. Webb has imaged it before, but newer spectroscopy helps scientists map what's inside, elements like nickel and iron, and how they're distributed. And here's the key part. Because a viewer literally joked about no smoking gun in the comments, even with better data, there still may be not one single signature that screams, this was definitely this exact type of supernova. Sometimes science is not a neat detective story. Sometimes it's narrowing the possibilities. And audiences who say, thanks for getting to the point without the hyperbole, are asking for exactly that tone. Show what we know. Show what we don't. Don't pretend certainty exists when it doesn't. Number 8. 10 times more distant supernovae than we've ever seen. Now we end with fireworks. Real ones. Using deep survey data, researchers identified far more supernovae in the distant universe than previously detected, some among the most distant of their kind. Why does this matter? Because supernovae are cosmic tools. They help us measure distances, trace star formation, and understand how galaxies evolved. If we suddenly have a much larger sample from the early universe, we can test our models harder. Were early stars more massive? Did they die differently? Did galaxies enrich themselves with heavy elements faster than expected? More data means less guessing. And now the headline moment. Webb detected a galaxy so far away that we're seeing it when the universe was only about 290 million years old. An early chapter of existence. At that distance, it's faint, it's small. It looks like a reddish blur. But the implication is enormous. Galaxies were forming, somehow, very quickly after the Big Bang. By the time you're watching this, the record might already be broken again. That's not hype. That's what fast science looks like with a telescope this powerful. A lot of you love the speed, but some of you asked for something different at the end. A moment to actually absorb what you're seeing, especially deep field imagery. If this update helped you, like the video, subscribe to BackSpace, and comment one more thing. Which discovery should be its own full episode next? Because Webb isn't slowing down, and neither are we.